All right. Thank you. Welcome back to our fourth topic for today. Gregory Perrine is an R&D research scientist at Georgia Pacific's Neenah Technical Center in Wisconsin. Greg is excited to share his passion for DOE with you by providing an example of a mixture process design with a short discussion of how DOE has been advanced within his R&D organization. So with that, Greg, we welcome you.
Well, thank you very much for the introduction, and a big thank you to Stat-Ease for having me present today. I also want to thank the rest of the audience for taking an hour out of their day to listen to me talk about mixture process design that I use within Georgia Pacific R&D to create value. And I'm also really impressed by all the other presenters that have gone today and yesterday. I can tell I'm definitely in I'll say the virtual presence of a lot of skilled practitioners in DOE, and I'm very humbled and honored to be able to end this conference with my talk. So a quick overview of the agenda for the presentation for today. We're going to take a little bit of time to talk about my background, who I am, my career so far, and some of my areas of expertise. We'll take a little bit to talk about an overview of Georgia Pacific, for those of you who don't know the company or don't know the products that we make. We'll take some time to talk about this mystic art of papermaking, because I know I'm not going to assume that many of you are well versed in papermaking or how paper is produced. So we're going to take some time just to get people grounded in the types of chemistry that we're working with and where in the papermaking process that we're going to zoom in on for my talk today. And then we'll take a little bit of time to talk about the actual design itself. We'll talk about some of the differences, more practical differences between a KCV design and a fully crossed quadratic mixture process design. We'll talk about the design objective, the design approach, a little bit of time on the design build. And then we'll really dive into the models. So we'll be able to take a look at the ANOVA tables together, the diagnostic plots, and really what the 3D models are telling us about our design space. And we'll wrap that up with some discussion on optimization and take some time to do some conclusions as well. And at the end of my talk, what I'm really excited about as well is to discuss a framework that I put together for how to advance DOE within an organization. And I use this framework to do some pretty fascinating, cool things as far as building a DOE capability within my R&D building. And the hope with this discussion is that I will provide all of you a framework for those of you who are passionate about DOE but are maybe on a team or within an organization that does not use DOE frequently. My hope is that you can use this framework to build some momentum in your organization for establishing DOE and really showing the value of the tool. And I'll give you some tips at the end for doing so that have helped me out as well. So with that, let's talk a little bit about who I am and my background. So as Sherry said, my name is Greg Perrine. I graduated from a university in Wisconsin about 8 years ago, and so far I have about 7 years of R&D experience. I started my career off at a company called Appion, which is a paper coatings company in Wisconsin. And there is where I started on their growth team within R&D, so doing new technology development and new product development. And then after about a year, I switched over to a different business unit within Appion called Encapsus, and they make microcapsules. And this is where a lot of my foundation for DOE was really set. I was also on the growth team within Encapsus, and that team really put a lot of emphasis on and value on the use of systematic experimentation to generate data-driven learnings. And this, like I said, it set the foundation for me for DOE. Within that team, I learned a lot about the fundamentals of DOE. And it's really also where my kind of passion area was ignited in the intersection between chemistry and statistics, and using both of them together to create value. And like I said, it's where I gained a lot of my foundational knowledge on DOE, both from just kind of standard kind of bread and butter factorial designs to response surface methods, and then also mixture and process designs. It's also where I was trained on the use of those tools as well. And the winding road of my career led me to Georgia Pacific, which is where I currently am. I've been here for about 2.5 years. And today I dabble in papermaking chemistry and also formulations chemistry as well. And it's at Georgia Pacific where I've tried to take some of my fundamental knowledge on DOE and my passion for DOE, and I'm trying to take on the role as a teacher. And I'm trying to take my learnings and really spread awareness and to teach others and empower others how to use the tool to create value in their role. Some of my knowledge areas, polymer chemistry, surface and colloid chemistry, and papermaking chemistry, all those are kind of intertwined in their own way. Also experimental design, obviously the use of DOE. And also I'm fairly well versed in data analysis. I also dabble in big data machine learning type tools and algorithms such as gradient boosting, random forest models, and things like that. I've been able to use some of those tools in my role as well. And I'm also currently leading a team called the Design of Experiments Knowledge Network. I promise that's a thing. I didn't just make that up. And we'll talk about what that group is and why it was formed in the last parts of my discussion. So anyway, enough talk about that guy. Let's spend a little bit of time talking about Georgia Pacific. So for those of you who don't know Georgia Pacific and doesn't know the products that we make, it is a US-based company with about 35,000 employees. And we make all different types of products within the kind of papermaking and cellulose industry. We produce building products. We also have a cellulose division that makes fluff pulp for things like diapers. We have a chemicals division. We also have a packaging division as well. And then we also have our consumer products group, which is where my role fits into. Now, Georgia Pacific produces a lot of very notable, well-known brands kind of sitting on your local grocery store shelves. We have our Quilted Northern Ultra Plush shown in that picture, our Brawny Towel, both very well-known brands, but also Angel Soft, Sparkle Towel, and then also Dixie Plates, Dixie Cups, and the Dixie brand is within the GP CPG group as well. And also our GP Pro business, so away from home, when you think of paper towel in a public bathroom or in a business, in a bathroom of a business, you will likely see our logo implanted on something within a bathroom of some kind, either a business or an away from home, because we are one of the leaders in the away from home market as well. Now, my R&D facility is a R&D facility for the consumer products group. So our facility, as Sherry said, is located in Wisconsin, which is where I'm located. And within this R&D facility, we have all different types of groups, from product development to chemistry development to consumer research. So it's a pretty diverse group of people up in our R&D facility. And my role within the company is I work for a group called the Chemistry Platform Team. And what our group is tasked with is basically any type of chemistry that's added to any of our papermaking operations. So tissue, towel, napkin operations, any of the chemistries that we add to our processes to either give the paper the properties that our consumers want, or any type of chemistry that's added to our papermaking assets to make our operations more efficient. And also any type of functional coating chemistry, such as for Dixie cups or Dixie plates, or any type of other coating that goes into our consumer products, our team is also tasked with having expertise on as well. So now that I've talked a little bit about Georgia Pacific and who we are and the products that we make and kind of how I fit into that team, let's talk a little bit about the mystic art of papermaking. Again, I don't want to assume that anyone here understands how paper is made or where it comes from. And so I wanted to kind of get us grounded in the papermaking process. And again, this is a 50,000-foot view of how paper is produced. But I want to start at the picture at the top left here. That's a picture of a group of trees. And kind of buried within these trees is a very useful natural ingredient called cellulose. And cellulose is a natural polysaccharide that paper is primarily composed of. And now what we do is we take these trees and we basically run them through, I'm going to call it a cellulose extraction process, which is a very complicated process to fit into one picture. But basically what you're trying to do is take the tree, you're trying to remove the bark, you're trying to chip the tree down into smaller pieces so they're easier to process. And then you run these pieces of wood through a digesting process and a bleaching process. And really what you're trying to do is you're trying to take that cellulose that's within the tree and you're trying to extract it from all the other ingredients that are also in the tree that are not useful for paper making. And what you're left with at the end of this process is a beautiful bright white fiber product that's composed primarily of our natural ingredient cellulose. And what you do is you take that fiber and you add it to water, and what you create is what's called a pulp slurry. And basically what you're trying to do is you're trying to disperse the pulp in water. You're trying to create a highly uniform dispersion of cellulose in water. And what you do is you take that dispersion and you run it through what's called the wet end of the papermaking process. And it's in this wet end of the papermaking process where basically the fiber is diluted with more and more and more water until you create a very low consistency, low concentration dispersion of fiber in water. And this is also where you add your chemistries to your process. So this is where you can add, for one example, something called a wet strength resin to your papermaking process. Now, when you think of wet strength resin, what I'm really talking about is if you kind of compare in your head, you have a piece of copy paper. When you get that copy paper really wet, let's say you accidentally spill your coffee all over your copy paper, which totally happens to me at least once a week, the copy paper tends to fall apart because it doesn't have any type of polymer that's helping it have wet strength. When you take paper and then you re-wet it, if it doesn't have any type of wet strength chemistry in there, it will tend to fall apart. Compare that to if you have something like a paper towel, right? So if you spill coffee all over your copy paper, you take a piece of paper towel, you wipe up your desk, you throw the piece of paper towel away, and you'll notice that when you get that paper towel nice and wet, it doesn't fall apart, or at least it shouldn't if you have a good quality paper towel, right? It absorbs that water and it still retains a little bit of that strength. Why it has those properties is because we add something called a wet strength resin that allows the paper to have strength after it is re-wet. You add this resin to the wet end of the papermaking process. So again, as the fiber is diluted down, you form it into a dispersion, and you add your different chemistries that will give your paper the properties that it needs. And then you take this pulp slurry that's been treated with our chemistries and you send it right over to the paper machine, which truly is a magical process. What you're taking is a very low concentration fiber slurry, and what you're doing is you're forming a mat of fiber, you are dewatering it, and you are drying it at extremely high speeds and high efficiency. And what you're left with is a nice, what we call base sheet coming off of the paper machine. You send that base sheet through a converting process where you either create it into a 2-ply or a 3-ply product, and you're left with this beautiful retail bath tissue Angel Soft product at the end. So that's the kind of general overview of the papermaking process and kind of seeing into the black box a little bit. But where again I want to focus our attention is the wet end of the papermaking process, because as I said, this is where we add our different chemistries to the process. And I mentioned a wet strength resin. There's a whole different variety of resins and polymers you can add to give your paper different properties. But this is where we're also going to add what's called a Debonder chemistry. Now, what is a Debonder? Debonder is basically a chemical means of reducing the strength of our paper. We're going to talk a little bit in the next slide on why we would want to reduce the strength of our paper. But I also want to kind of get us grounded in the chemistry and kind of the why here. So why a Debonder reduces the strength of our paper, we first have to take a minute to talk about where the strength of our paper comes from. So in this picture here, I have 2 cellulose fibers. I really don't want us to get bent out of shape about the functional groups hanging off of here. These are the things that I like to look at, but again, I have a chemistry background, not going to assume that anyone enjoys looking at this stuff. So don't get bent out of shape about what these functional groups actually are. What I want to point out to us is these functional groups hanging off of these 2 cellulose fibers. When the cellulose fibers come into close contact with one another, those functional groups will form a network called a hydrogen bonding network, which is basically these functional groups will quote unquote bond to one another, not in a permanent way, but in a reversible way. And this is called a hydrogen bonding network. And so really what it is those fibers are really interlocking with one another. They're having this hydrogen bonding network forming between the cellulose fibers. And of course, when you make a mat of fiber, you're also creating some fiber entanglement as well. And those two forces are what's really driving the paper strength. Now, what does a debonder do? This is a picture of a debonder chemistry added to our process. And again, really don't want you to worry about this molecule. I know it looks fairly complicated. I really want to point out two things. The first thing I want to point out is this chemistry has what's called a positive charge or a cationic charge associated with it. What I didn't mention yet is that cellulose, when it's dispersed in water, has a negative charge naturally associated with it. So we're adding a chemistry that has a positive charge because we know that it will be attracted to the negative charge on the cellulose fiber. So when we add a chemistry, what we're wanting to do is have that chemistry actually go to the fiber and not to remain in the water. Because if it's remaining in the water, it's not going to come in with the actual paper product itself. It's just going to be kind of circulating in the water of the paper machine, and it's not going to give you the functional properties that you want. So I want to point out that positive charge. The other thing I want to point out is this chemistry has these long fatty tails associated with it. And what those fatty tails do is they get in the way. What they do is they prevent that close contact between the two cellulose fibers, and they prevent that hydrogen bonding network between the fibers as well. And what you do is you prevent that hydrogen bonding and you reduce the strength of your paper product. So again, I don't want you to get bent out of shape about the actual chemistry, the functional groups there. Those are not that important, but I want you to have a key takeaway that debonders are added to the wet end of the paper machine to decrease the strength of your paper. Now, why would we want to decrease the strength of our paper? The important relationship that I want to point out is that there is an inverse relationship between the strength of paper and something called the paper softness. There's an inverse relationship. Now, this graph shows that as you go from left to right, you increase the debonder dosage. We already talked about how by doing that, you will decrease the paper strength, which is this blue line. You increase your debonder, you reduce strength. What you're also doing is you're increasing the paper softness because of this inverse relationship. Now, paper softness is a key attribute for many of our products. Again, kind of thinking back to a piece of copy paper because it's kind of what I have in front of me. You have a piece of copy paper. It's fairly strong when you compare it to a piece of facial tissue, right? Copy paper is pretty strong, facial tissue is pretty weak. Well, copy paper is not as soft as a facial tissue, right? You probably wouldn't blow your nose with a piece of copy paper unless if you were really desperate, because it wouldn't give you a very soft experience, right? Versus facial tissue is very soft and therefore it gives you a more positive experience if you have to blow your nose. One of the reasons for this, not only being because the fibers and the fiber furnish is a little bit different, but because one of them is much stronger than the other. And it's because of this inverse relationship. So again, another key takeaway that I want you to have is debonders reduce strength, and by reducing strength, they increase the paper softness. And again, softness is a key attribute for many of our products. And debonders give you a lever for strength control on your paper machine. So let's take a moment to talk about debonder formulations. So debonders are not just one chemical compound. It's not just that chemistry I showed a couple of slides ago. It's actually a mixture of charged and uncharged surfactant materials. And the issue that we have is we actually have a range of debonder products that we've developed in-house over the past couple of decades. But it's not really clear why one product outperforms the other. All these products have a little bit of a different ratio of our charged and uncharged surfactants. We know that they work fairly well, but it's not really well understood why. What is actually driving debonder performance? And the hypothesis that I had is if we could understand the interaction of our mixture components a little bit better, could we build a better debonder, and can we learn something along the way about our system, about our chemistry? So this kind of leads to my problem statement. We don't really understand the interaction of our mixture components and how they interact to impact debonder performance. And the mixture space was largely unexplored. So the objective of my study was to use a design of experiment approach to characterize the mixture impacts on debonder performance. In this particular study, I have a 3-component mixture design, so components A, B, and C with slightly different ranges for A compared to B and C. But I also want to study not only how these 3 components are interacting to impact my Debonder efficiency and performance, I want to also understand how the add-on rate of my Debonder also changes performance. So changing the components of my mixture, but also changing how much of that mixture I add into my process and how these things influence the performance. So I have the 3-component mixture, and I also have one process factor, which is my add-on rate, which we use pounds per ton as our units. Now, because we have a 3-component mixture, we're going to use what's called a mixture design because that's the most appropriate. Because I also want to study a process setting, we're going to use what's called a process mixture combined design. Now, for those of you who have never used Design Expert, I'm assuming most of you have. If you're trying to look for where mixture process combined designs are within the Design Expert toolbox, I want to just take a couple seconds to kind of show you where it is in Design Expert. So this is in the Design Expert 12 software. Again, we have our kind of standard factorial designs, our response surface designs, and our mixture designs. If you want to run a mixture and process setting combined design, it's going to be under custom designs under optimal combined. You're going to be shown this screen. We're using a 3-component mixture design. And of course, we're studying one numeric factor as well. We set our components A, B, and C, and here are the ranges. And they all add up to a 100% of the mixture. We don't have any funny constraints to use. And also we're studying our process setting, which in this case is our dosage of the overall mixture to our process. And we're studying between 2 and 15 pounds per ton. Now I want to take a brief moment to talk through some of the practical differences between a KCV design and a full quadratic design. And I really want to encourage you, for those of you who want a really deep dive into KCV designs, if you want to know more about the math or the design structure or the underlying statistics, Stat-Ease has a lot of great presentations that really dive into this depth of what a KCV design is. And in fact, if you tuned in last year to last year's DOE Summit that was hosted by Stat-Ease, Professor Vining, who was one of the creators of the KCV design, also gave a really great overview of this KCV design. It's actually where I first learned about it, and I listened to that presentation by Dr. Vining, and then decided this might be a really good fit for some of my experiments that were coming up at the time, and this was one of them. So again, if you want a lot more depth, I really encourage you to take a look at those presentations. Stat-Ease has a lot of really great material. But a KCV design, kind of in a non-statistician nutshell, is a compromised design where certain mixture model terms are crossed and some are what's called additive. And really what you get is a design with the individual mixture components linked, and some of the mixture components are linked to the process factors, but it's not a total complete cross of all the mixture terms with the process terms. Now, said in kind of a practical way, if you go into Design Expert and you use my design, so a 3-part mixture and a 1-part process design, and you ran a fully crossed quadratic by quadratic design, what you get is this model term table at the left. And again, what you have here is, again, you have the individual mixture components. You have the quadratic mixture components, so you have the nonlinear blending terms. So in this case, AB, AC, and BC. You have the individual mixture components linked with the process component, which is AD, BD, and CD. But you also have some of these higher order terms where you're studying the nonlinear blending term crossed with the process factor, the individual mixture terms crossed with the curvature term, and the nonlinear blending crossed with the curvature term. So you're getting some really high order terms here, which again, if you think your system is going to exhibit those kind of more complicated higher order terms, then this design is appropriate. But what I like about a KCV design is it kind of simplifies the design structure. You keep a lot of the really valuable mixture terms, the nonlinear blending terms. So again, we're keeping AB, AC, and BC. You're getting the individual mixture components also crossed with the process setting, and then you're also getting this curvature term for the process. So it's a much more simplified design structure, But what I really like about it is I had a hypothesis that this type of design would be able to really characterize my system pretty well, and I might not need some of these really high order terms that you get from the fully crossed design. And in a practical way, again, if you're going to run a fully crossed design, you're going to get a lot more model terms. So if you include the model terms, again, plus the replicates and the lack of fit points that design expert recommends, you're going to be at about 28 runs, which is not too bad. But if you run a KCV design, again, with less model terms that you have, including the replicates and the lack of fit points, you're at 20 runs, which for us is about 30% less, which for our lab, that saves them a whole day. So they were very happy that I ran a design where I could cut out one day of runs, and they were really happy with that. And what's really interesting is the KCV design saves you a significant amount of runs, but especially when you add in more mixture terms and more process terms, right? So I was just using a 3-part mixture design and 1-part process design, but if you had 4, 5, 6, 7 mixture components and more than one process setting, a KCV design is going to save you a significant amount of runs. So hopefully that was a decent kind of practical overview of what a KCV design structure looks like and what the KCV design, how it compares in the number of runs with a fully crossed design. Again, definitely want to point out, if you want more information on these types of designs, Stat-Ease has a lot of great information, so I would definitely recommend that. So I wanted to show the design table. So this is the table produced by Design Expert for my KCV design. And why I also wanted to show this table is this is actually the design table that I showed internally to some of our R&D folks when I was talking about this design. The colored rows are the replicates, so there's 4 replicates. And why I wanted to point this out is if you look at my KCV design, when you count up the number of different formulas that we're using 11 formulas. So 11 different kind of composition ratios are used in this design. If you look at the number of add-on rates that we're using, we're at 9 different dosages. You throw in that there's 4 replicates, we're at 19 runs. Now, why I was showing this to a group within my building was I was saying, okay, let's say I wanted to study these 11 formulas. Let's say I wanted to study them with what we call a typical dosage curve, which for us, if we're doing like a Debonder study or a different chemistry study, and we want to run something between 0 and 15 pound per ton, what we'll do is we'll do a dosage curve of, let's say 3, 6, 9, 12, 15. So let's say we did a 5-point dosage curve with 11 different formulas. We'd be at 55 runs. Add in 4 replicates, and we'd be close to 60 runs to investigate this many formulas with our kind of standard 1 factor at a time approach. And I can do it in 19 runs. So I was trying to showcase this is the power of a DOE. You get so much more information, especially with any type of design, but especially the mixture space, so much more information about your different formulas for only 30% of the runs, which when I show that to people, they're just like, what? Which is why I love DOE and why I could talk about it all day. But I know I don't have time to do that. So we have our design build, and now what are we measuring? We have 2 responses that we're going to be looking at. One is strength reduction. So I talked a few slides ago about how Debonders, again, are added to the wet end of the papermaking process to reduce our strength. So now we'll measure how much strength we are really losing by adding our Debonder. So what we do is we take a piece of, we take paper with no Debonder added to it, we create a handsheet, and we have our strength of that paper. And then we make a set of handsheets with the different Debonder formulas at the different add-on rates, and we basically calculate what is the reduction in strength that we're seeing compared to our baseline. And that'll tell us, again, how effective is the Debonder formulation. The other piece that we measure, which this is the first time I talk about it, so I want to take a minute to kind of talk about what this is what's called Zeta potential. Now, when I talked about cellulose fibers in water, I mentioned that cellulose fibers have a natural negative charge. So it would have a negative Zeta potential. Again, Zeta potential is the fiber surface charge measured in millivolts. So a fiber dispersed in water would have a negative charge. And when we're adding a positively charged chemistry to our system, what we're hoping to see is if that chemistry is adsorbing to the fiber, if it's going to the fiber, you're going to see a change in the fiber surface charge, and we can quantify what that change looks like. And what that will tell us is our chemistry effectively adsorbing to the fiber? Is it going to the fiber, or is it staying in the water? Because if you add a positively charged chemistry and it's just staying in the water and it doesn't go to the fiber charge is not going to change. So we want to study how is the debonder that we're adding changing the fiber charge, and we can quantify this and potentially model it. So those are the two responses that we are going to be taking a look at. Now we get to dive into the actual models themselves. So this is an ANOVA for the KCV model for strength reduction. See that here. A couple of things that I look for when looking at an ANOVA table and the fit statistics. Again, if you've been through a Stat-Ease training, they train you on how to look for these things. But again, just to kind of refresh ourselves, first thing I look for is that model p-value, right? So far below 0.05. So I know this model is highly significant, very low chance that this model is just due to random noise. Lack of fit is not significant, which is great. It tells me that my data is not really deviating from my model relative to the pure error that I found in the experiment. So, which is good. We want our model to actually fit our data. So not significant lack of fit is great. A couple of other things that I look for. So the predicted and adjusted R-squared. Adjusted R-squared is very healthy, right around 0.93. And a predicted R-squared of about 0.75, which again, those are in reasonable agreement with one another. And for this lab study, predicted R-squared of 0.75 is actually fairly good. So our any papermaking process is going to have some inherent variability coming with the furnish and how the handsheets are generated themselves. So a predicted R-squared of 0.75 I was very satisfied with. The other thing that I look for, so adequate precision, stat or design expert kind of prompts you on what the ratio should be, so 4 or greater, which of course we're far above 4, so happy with that. The other piece that I like to look at, and I don't talk about in the discussion today, is how you assess the power of your design, so doing a power evaluation. And before I ran this study, I had an approximation of what my standard deviation would be. And what I found from the fit statistics and the standard deviation generated in this model is that the standard deviation that I approximated for this process was fairly close to what I found during the actual study, which is good. It tells me that during the design, I didn't have any any spikes in kind of noisiness in my data. Wasn't any more noise that I wasn't already anticipating when I put the design together and evaluated the power. So I was satisfied with that as well. So it seems like we have a statistically significant model. So let's go to the diagnostic plots. Now again, these diagnostic plots are shown for every model in Design Expert, which is great. Kind of moving from left to right here. So we look at the normal plot of the residuals. That passes what I think Design Expert or Stat-Ease calls the fat pencil test. So no concerns with non-normality of my data. The residuals versus run, looking for any time effects in the data. I didn't see anything that was troubling to me as being a time effect going on. No transformations recommended by Design Expert. So they show this box Cox plot, and again, no recommended power transforms. Taking a look at Cook's distance, there's a couple of points that are at least getting kind of close to that red line, but when you take a look at the DF fits and the DF betas, there's no data points that stick out as kind of being overly influential on the data and that seem to be skewing the models in any way that I wasn't comfortable with. So nothing really troubling stuck out to me. So the model seemed statistically significant. It passed kind of all the diagnostic checks that we go through. Let's talk about what the models are saying. So just to remind ourselves, we are looking at a strength reduction model. And this picture on the left is showing our 3 components contour plot of our mixture design. So we have our 3 components, component B, component C, and then component A at the top. And what I'm trying to look for, other thing I want to point out is this contour plot is at 1 process setting. So for this, I picked 7.5, which is pretty much right in the middle of my design space. So just to see the behavior of the 3 component mixture at 1 process setting. I'll point out in Design Expert, it's very easy to take this process setting and to change it to see how that 3D model or how that contour plot is changing based on the process setting. And what I'm trying to look for here, again, the higher our strength reduction, the more efficient and effective our debonder is. So the more it's reducing the strength of our paper, which is good. That's why we're adding it. And what I wanted to look for is there a region that seems to have the maximum strength reduction, which if you see the contour plot is right in this orange region here, which I cannot emphasize enough that this was a key learning for us for two reasons. Number one, this region was previously unexplored with any of our other debonder packages or any of our other experiments in the past that I could find. So an unexplored region here, which seems to give us the maximum amount of strength reduction for our debonder. The other piece that's really important from this, this whole contour plot, is we've never characterized this A and C interaction before. In fact, we've never characterized any of these interactions before. So the fact that we could generate a sound statistical model that characterizes this complex interaction between surfactant materials is a really huge learning for us. And if we take this contour plot, we can create a really nice 3D model. And again, what we see is this little hump towards the side here between our A and C component line. And again, we find that there is a optimal region right in here, probably at about 40% of A and about 60% of C. So we have our strength reduction model. Let's take a quick moment to talk about our Zeta potential model. So we have our Zeta potential model. Again, going through the same checks that we look for. Model is highly significant, which is great. Not significant lack of fit, so the model seems to be fitting our data very well. Predicted R squared and adjusted R squared, very healthy, above 0.9, which I was very satisfied with. Adequate precision looks great. And again, net standard deviation, just to do a quick check, and that's fairly close to what I was estimating for this design. So again, was happy with that. I don't show the diagnostic plots for the Zeta potential model just for the sake of time, but just, you have to trust me, went through the same type of checklist for the diagnostic plots and saw no significant issues. Now, what this is showing is the impact of the 3-component mixture design on our Zeta potential, or the fiber surface charge. Now, like I said, fiber dispersed in water with no chemistry has a naturally negative Zeta potential. And what we're trying to see is how this 3-component mixture at one process setting is influencing the charge of the fiber. And a very interesting finding that if you take a look at this contour plot and take a look at this 3D model, looks very similar to the strength reduction model, which tells me that this combination of A and C has the maximum amount of chemistry going to the fiber. How we see that is this is actually a positive Zeta potential. So we see down here, this is a -40 Zeta potential. Up here, we're getting into that maybe +5 to +10 Zeta potential, which tells us the fiber is getting more and more and more positive because more and more of our debonder is going to the fiber. Now, don't overthink that too much. What I can't tell you is what each of these individual components are, and some of them are charged and some of them are not charged. So can't tell you what they are. But again, just want to say we've never documented the dynamics of this mixture system and how it influences strength reduction, but also the charge of our fiber. So just the characterization alone was a key learning for us, but also this kind of link between the Zeta potential and the strength reduction, although it's not surprising, was good to find. It kind of verified some of our hypotheses coming into the experiment. So the question is, can we put all this together? So I showed you 2 responses. There was a handful of other responses that I had taken for this experiment as well. Can we put it all together and try to have Design Expert tell us, give us a direction for the maximum amount of strength reduction for our debonder? So now the really exciting part, which I know you're all on mute, so you can't give me a drum roll, but the optimization piece, one of my favorite things to do. So what we asked Design Expert to do was to give us a debonder package or a list of debonder packages, so a couple different solutions that would give us a maximum amount of strength reduction while also looking at some other responses as well. What I could also do is, because this mixture design covered such a robust design space, is some of the other Debonder products that we currently have fit within this design space. So what I could have Design Expert do is, if I know the ratio that's in some of our other Debonders that we already have in-house, I can have Design Expert predict for me, what do I think the performance of those will be? So I used two of our kind of in-house Debonders, Incumbent A and Incumbent B, and I had Design Expert predict what it thinks the performance will be based on this experiment, which is the blue line and the orange line. And I have three different optimizations that Design Expert gave me as solutions to my objectives in the optimization tool. So what I want to point out here is, well, number one, this is all based off model predictions, right? So I did not run Incumbent A or Incumbent B during the experiment, but again, this is just predictions based off of the model. So how I would compare our two incumbent chemistries to some of these optimizations is, I would say, okay, let's set a target. Let's say I want to reach 50%, what's called, well, I call it breaking length reduction. It's basically 50% strength reduction. And what I would look at is, how much of the first chemistry do I need to add to hit that reduction? So if we look at that blue line, we'd have to add 8 pounds per ton. So follow that blue line from the target down to the x-axis, which is where our dosage is. We're at 8 pounds per ton. When I look at my second chemistry, that orange line, how much of that chemistry would I have to add? Well, about 6.5 pounds per ton. Let's look at the most, what I'll call optimal for strength reduction, our optimization 3. If I wanted to hit 50% of my strength reduction, I'd only have to add just a little over 4 pounds per ton. So when you're comparing to our first incumbent, that's 50% less Debonder. To our second incumbent, that's 40% less Debonder. So we have to use far less of the Debonder chemistry to hit the same strength reduction, which not only has opportunities for significant cost savings, but also the more chemistry you can pull out of your papermaking process, usually the better. Because some chemistries not only impact your paper properties, but they also impact your machine runnability. And Debonders, kind of in general, don't always play well with other chemistries in your process. So sometimes they can cause machine runnability issues. So the more Debonder we can pull out, the better. So a really significant opportunity for cost savings and just pulling chemistry out of our system. And it was found by this optimization feature within Design Expert. And so really happy with the results of this study, kind of putting our different responses together and using this KCV design to point us in a new direction of research for Debonder formulations. So just to wrap up this discussion on the DOE, again, we leveraged a KCV design to explore a largely uncharted formulation space. We generated statistically significant models built for our key responses, and the optimization showed a significant opportunity for more efficient Debonder formulations and potential cost savings. So overall, really happy with the results of this DOE, and I'm really happy to share these results with you. Now to move on to the last part of my talk, which I'm really, really excited to talk about. This is going through the framework that I had put together when I first joined GP R&D. Now, this framework is not new, it's not novel. I'd argue most of it's pretty much common sense. But this framework was built as a list for the recommendations to build a DOE capability within your organization. I argue that if you do these three things, you have a really good shot of building a DOE capability within your organization and supporting that capability long-term. But for a little bit of history, when I came to GP about 2.5 years ago, when I came to our R&D facility, there was really little knowledge of how to use design of experiment outside of maybe 2 or 3 power users in our building. There wasn't a lot of understanding of really what a DOE is, when to use it, the pros and cons, the questions to ask, and more often than not, people used kind of a standard one factor at a time approach, which was kind of a culture shock to me, because as I said, when I was at my previous company in Capsys, we used DOEs all the time. And in fact, we used them so frequently and understood the value of them, it was basically you use a DOE unless if you have a good reason not to. But when I came to GP, it was basically you use one factor at a time, why would you use DOE? So it was kind of a culture shock to me. Again, not saying it's right or wrong, but it was definitely, like I said, kind of a shock to my system. And I'm so passionate about DOE, I was like, I got to do something about this. So what I did is I thought about how can I help kind of build the capability and spread awareness of DOE within my organization. And what I did was I came up with this framework. So I argued if you want to build the capability to run DOEs in your organization, first you have to start with teaching, right? People aren't going to run a DOE if they don't know what it is. So you have to teach people the terminology. You have to teach them the foundational statistics, the questions to ask, the what, the how, the why. So you have to have people trained to actually use the tool. But then you have to empower them to use the tool. What I mean by that is I could walk up to somebody and give them a statistics textbook. I could give them John Cornell's textbook on mixture designs, and I could walk them through what the theory and the fundamentals are. But if I don't show them how to use it, they're never going to use it. So you have to teach people, but you also have to empower them to use the tool. So you have to give them practice examples. You have to give them hands-on exercises. You have to connect the theory, connect the actual DOE tool to the work that people are doing in their role. And I'd argue one of the most important things I think you have to do is give them an easy-to-use software. So if you teach them, but you give them a software that's cumbersome, that doesn't help you, if it doesn't kind of guide you from the beginning to the end and prompt you with, prompt you with questions and, hey, what type of design are you trying to run? Oh, don't use this design, use this design. Or even tell you, hey, you're about to do something kind of dumb, which I've used other DOE softwares. Many of them are pretty passive aggressive. They'll say, you want to do that? Okay, go ahead. Whereas Design Expert will tell you, you're about to do something wrong, maybe reconsider, which is why I love the software. It's very easy to use and very user-friendly. And the last thing you have to do is you have to teach, empower, but you have to support them. Because as we all probably know, you can teach someone how to use a new tool, but if you don't get support from a network of people or a support from managers, if they don't say yes to you using the tool in your current role, then you're not going to get a lot of experience with using it. And in a year from now, you're probably never going to use it again. So you have to build that network of users. You have to get support from management to actually use the tool. And you have to connect people together, especially if you have a group of new users. And I highly recommend if anyone on this call is thinking about getting people trained in the use of DOE within their organization, build a support network, a network of users. Keep those people connected together to challenge one another and to continuously learn together and to continuously improve on how to use the tool. But not only that, like I said, within our R&D building, we had kind of local experts on how to use the tool. So what we did was we built a support network both for new users and we connected those people to the local champions who are experts in the tool, again, to get that continuous learning. And all this facilitates long-term learning. And I argue that you have to support people. So this is what led to the creation of what's called the DOE Knowledge Share Team within R&D. It's a group of about 30 people within R&D and actually outside of our building as well. And basically what we all do is we meet about every 12 weeks and we basically just practice case studies. We talk about designs. We talk about, in my situation, would a DOE be most appropriate? Or we talk about how people have used DOE to create value and what the findings were. And honest to God, pretty much this conference, just with newer users, but talking through, again, example after example after example of how people have used the tool. So this framework I kind of put together, and I basically pitched it to 6 of the directors in our R&D building. And I said, hey, I'm generally new to this place. I don't think there's a lot of capability to run DOE. I think it's a very valuable tool. It's one of the most effective tools that we have. Here's my framework for how to build the capability. Will you resource this? And will you help me out? And they all approved. So what I said was, let's get people trained and let's get people empowered to use it, which led to my recommendation to actually bring Stat-Ease into our building. This happened early last year, and they did their experimental design made easy training. Again, they taught the fundamentals, but they also went through practice examples. Their software is very easy to use, and with the examples they used and the how well they taught the terminology and everything else, the foundations of DOE, the training that they gave was very positively received, so very well received by the 25 people that were trained within my building. And these 25 people spanned all different groups within our building. It wasn't just scientists, it was chemists and engineers and scientists and consumer scientists and consumer researchers. It was all different types of people. And there's even a couple of people from manufacturing as well came for that training, and they all gave very positive reviews of the training. And then we formed the DOE Knowledge Share team after that training, and again, gave opportunities for people to ask questions and to network with one another and challenge one another and to kind of continuously learn and grow and how to use the tool. So what was the output of that? So we had the framework, we got trained. Since early last year, we've run 30 DOEs within our R&D facility in the last probably 18 months. 30 DOEs. That's more DOEs in the last 18 months than have been run in the past 15 to 20 years within our building combined. So a substantial increase in the use of the tool. But not only that, 16 other DOEs were at least planned or analyzed as an alternative approach, which is great. So almost 50 designs were either completed or at least talked about and analyzed as an alternative. And to me, it's not really all that important how many DOEs are run. I think it's great, but it's also, are people using the tool to create value? And the answer so far has been overwhelmingly yes within the building. And I really want to point out, Stat-Ease has been a really great partner through all of this. As Martin knows, as Sherry knows, as other folks within Stat-Ease know, what I didn't point out is all 50 of those DOEs I was pulled into. I was pulled into at some point, either in the planning or the analysis or the model interpretation, the discussions, all of it. And so because I was pulled into all of it, and again, I have experience with DOE, but I'm not an expert. So Stat-Ease has been a great partner, and if someone asks me a question, and I've gotten some really off-the-wall questions before, Stat-Ease has been really supportive in answering all my questions. And so I really can't say enough good things about the company. They do a great job of teaching, but they also support people long-term with the software and with their questions. So yeah, really excited to kind of share this with you. And again, I really hope that people use this. Again, this is not mind-blowing stuff. It's all pretty common sense. But I hope people can kind of take this and use their own passion for DOE to advance the capability within your organization. A couple of tips, kind of tips and tricks just to finish us off. The things that I learned kind of while implementing DOE in my building is you have to track the number of designs. I cannot emphasize that enough. So, and again, it was fairly easy for me because again, people pulled me into most, if not all, the DOEs that have been run over the past 18 months. And again, so I had a pretty interesting opportunity to be able to track the number of designs. So if a design was being planned, I would track it. If it was in progress, I would track it. If it was completed, I would track it. And again, even if the DOE isn't run, did people at least analyze one as an alternative? And that's another point I really want to emphasize, especially if you're in an organization where one factor at a time is the standard. Are people at least thinking about, okay, with this system, with these inputs that I'm trying to study, with these objectives, how would I think about this as a DOE versus a one factor at a time approach? And are people at least drawing up information on both of these approaches? And I can't emphasize that enough. Some people think like, well, if a DOE is not going to fit, I'm not even going to think about it. No, please think about it, because the more you think about it, even if you're not ultimately going to run one, it's going to build repetition. And repetition, of course, builds mastery. So the more people are thinking about it and able to answer, the questions for setting up a DOE, even if they don't end up running it, at least take time to draw one up and then pick the best choice. And the other part is, if the design is completed, capture the value. Did you find interactions in your DOE that you would not have found otherwise, right? We know DOE versus one factor at a time is the only way to find interactions. Well, did you find one? Did you solve a very, significant business problem with a DOE? Did you find like an optimization that you wouldn't have been able to find before? And loop those numbers back to your stakeholders. So when I pitched this framework and this training to our directors, I was able to loop back with them later that year and say, hey, here's how many designs have been run. here are the different, here's the business value of all these experiments. Here's what we found. And now people see that they invested time and money into your training and it's paying off. And the other reason why that's so important is because if you need more training, so if you're kind of graduating from the factorial designs, now you're starting to want to run more response surface designs or mixture designs, it's so much easier to justify to people why they should invest more in training because you've already told them how their original investment is paying off. So it's so much easier to justify more training, at least in my experience so far. So with that, that ends my kind of soapbox talk about DOE and why it's awesome and kind of the progress that we've made so far in the past year and a half here at my R&D facility. With that, that's all that I have. So questions?
Awesome. Thank you so much, Gregory. That was thoroughly interesting. I'm going to start with a couple of questions about the experiment first,
Sure.
and then we'll get into questions about the management part of it. So a couple people noticed that you hadn't removed at least one non-significant interaction coefficient from the model of the first response. Did you consider doing that? Did you try it and see did it help the predicted R-squared or anything?
No, that's a great question. So we can go back. Sorry, it's a little.
Yeah, it was a little ways back there.
Yeah, so this AB term?
Yeah.
So actually, when I removed the AB term, it actually didn't influence the predicted R-squared all that much. It stayed relatively the same.
Yep.
And because it's a lab study, again, I don't have such, I guess, hard black and white rules of if it's a p-value of above 0.05, I never include it, or, to me, if it's a lab study and I'm more exploring, I will keep some terms that are kind of close to that 0.1. Now, the other thing I really want to point out about that, though, before I get darts thrown at me, that AB term was not that significant for strength reduction. If we recall from this 3D model, the AC term is really where that maximum strength reduction was realized. The AB term wasn't all that significant. Again, yeah, you get some of this nonlinear blending going on here. But when I was looking at strength reduction, this is really where my region was going to be. So that helped me sleep a little bit better at night, knowing that I was keeping that AB term in the model. But if this was actually switched, if my AC, or if let's put it this way, if AC, which is where my maximum strength reduction was, if that p-value was very high, then I'd be very cautious about keeping that in the model and knowing that, I'm having an optimization zone here, but I have a pretty dodgy p-value for this term. So that's kind of how I justified it. I could definitely be wrong, but that's how I kind of thought through it. But yes, very good catch. People were paying attention.
Yeah, a couple people caught that. So I'm going to throw in a comment on that. A few years ago, I went to my favorite conference, which is the Fall Technical Conference, co-sponsored by a couple of ASA divisions and ASQ divisions. And a guy had done some research on the effect of model reduction. And the conclusions, going straight to the conclusions, he found that if you only had one or two terms that were non-significant in the model, removal of those terms had minimal effect on the predicted R-squared. But if you had like around a third of your terms or more that were non-significant, then removal of that group of terms did have a big impact on the predicted R-squared. So I've kind of kept that as a little rule of thumb and a justification for myself to not worry about one or two terms, but definitely as there's a group of terms, then the impact is bigger and bigger.
Yeah, absolutely. And I want to point that out too. I mean, I did go through the model reduction algorithms that Design Expert has to pick out this model. And I've actually definitely had examples in my experience with other users within the building. There have been times where I'm looking at people's ANOVA tables and I'm like, wait, there's like 6 insignificant terms here. Like, no, we got to remove some of these terms out. because it'll bolster, the fit statistics of your model. So wanted to point that out. Yeah, I did go through the model reduction, and yes, of course, recommend always doing that. But for this particular study, I kept that in there because it was kind of right on that threshold. And being a lab study, I decided to keep it in. But great question.
Yep. And a couple comments from John Davies, relevant here. Sometimes reducing the model terms, such as a cross term, will allow main process effects to come into the model. Sometimes I get a better model this way. So yeah, certainly
Sure.
with this combined model thing, that could be some interesting things going on there.
Sure.
He also says your project highlights a great feature of mixture DOE. Mixture DOE greatly increases the chances for unexpected discovery because it allows for efficient exploration of regions of the design space that would otherwise remain unexplored. This is especially valuable for areas of the design space that, based on existing subject matter expert intuition, are thought to be of no value.
Absolutely. I would 100% agree with that, yes.
Yeah. Let's see, I agree completely with your methods for promoting DOE. I've been in the same situation. For me, the key was showing them the wow factor early on. By wow, I mean showing them the efficiency and potential for unexpected discovery before getting too bogged down in teaching stats. Also, I had to spend energy reassuring the experts that DOE supplements what they do. It does not replace physical knowledge. How did you handle it when the SMEs felt that the stats methods might be somehow replacing the value of their knowledge? Did you have any of that?
I would say actually not really. I think I had a pretty easy time convincing people because I think DOE is kind of one of those things where, and maybe it's the dynamics of my building too. There's a good group of scientists who are been in the industry for 20, 30, 40 years, and those are the people I consider the kind of top experts within R&D. And the interesting thing is, especially within my building, those people have heard about DOE before. They were around when kind of DOE was starting to take off with kind of the quality movement and things like that. So they've heard of DOE. So I didn't have a hard time, I think, pitching it to them because they already kind of knew what it was. But they also agreed with me that there really wasn't a whole lot of capability, especially with younger engineers and younger scientists, to use the tool, because it's not something that, as we all know, it's not really something that you learn about in undergraduate or even maybe graduate school, unless if you're kind of unless if your education's in statistics. So I guess all that being said, I didn't really get a whole lot of pushback about, did people think that this was going to somehow replace their areas of expertise? Because really what I've also pitched to people as well is when you are kind of scoping out your design space. So if you're studying a process and you have really, you have no idea what the factors are, you have no idea what the levels that you should study are, that's really only something I think, or not only something, but one of the things you should talk with the experts about, right? So they'll know based on their experience, yeah, if you're gonna study this factor, what we found in the past that, this is kind of your factor range that seems to give you, a good outcome, or here are kind of your disaster zones, or especially if you're studying a fairly new system, or if you've never run a DOE before, when you think of something like a screening design where you're looking at 8 factors that are all varied randomly throughout a design space, we've had people actually go to experts before and say, hey, are there any of these combinations where we think we're really not going to make a good product, or is kind of in that, in that disaster zone? So I think in my experience so far, people have been actually just really helpful towards others using the tool, and don't really see it as a replacement. So
yeah. And Michael Bradshaw did comment in his conversations with people, the 55 run versus 19 run example can sometimes shut down conversations with their teams because they don't trust it. We manage that by saying that this is a starting point, and they can come back and do the extra runs later if they are right and more information is needed.
Yeah, no, I totally agree. I don't think I tell people design's not a magic bullet, right? It's not like you do one
Mhm.
design and now you have everything figured out. So definitely further runs to both verify your models or kind of zoom in on a design space that you find interesting. Um, yeah, definitely it's not a one size fits all magic bullet that cures every problem. So yeah,
Yeah.
I agree with that too.
Yeah. Can you take a minute to explain this contour graph that's on your screen right now, and how those the 10 to 100 for factor A and the 0 to 90 for B and C? Just give a little show and tell and interpretation there. Some people aren't familiar with reading that graph.
This graph here?
Yep, yep, yep.
Sure. So what this is that this is the three-part mixture design space. So if you recall from the ranges that I had set before, component B runs from 10 to 90%. So here, all the way at this corner is where B is at 90% and A is at 10%. Over here in this corner, component C is at 90% and A is at 10%, right? Because it's 100% of the mixture. As you move along this line, you're substituting component C for component A until you get to this corner, which is, again, I studied component A from 10 to 60%. So here I have only component A and component C. And then as we move along this line, this is component B getting substituted out for component A until we hit this corner. And then again, in the middle, we have an equal mixture of the three.
Mhm.
And what this is telling me is as I substitute components out for one another, what is happening to my strength reduction. So the way to kind of read this line to this line, again, I mentioned that the kind of optimal point right about here is at about 45% of A and 55% of C. So right along this line. And then of course, if you're looking at that in a 3D model, moving from C to A, you follow along this curve here, which is where our maximum is, right about here.
Yep.
Does
And
that help?
yep. And those the zeros on the left and right, that is just kind of your base of component B. Starts at 0 on that flat line and goes to 90 at the opposite corner. You know, as you're going from 0 to 90%, kind of diagonally across that.
Yes. Yep. This is also, it's kind of reminiscent of like a tertiary diagram, which
Yep.
for chemists or those in kind of the chemistry art, tertiary diagrams is something we learned about, I mean, a long time ago. But that's kind of how you read kind of mixture component diagrams. The other nice thing about Design Expert I point out too is, especially when I was first learning about mixture designs, I had a hard time kind of reading what each of these are. You can put little flags throughout here in Design Expert, so you can right click and put a flag down, and it'll tell you what the composition is at each of these points too. So that also helps.
Yeah. There was a question, did you predict the binding reduction in the last slide manually from the equation, or was that from Design Expert?
The strength reduction?
Yeah, I think so. Sure. Yep.
Breaking length, yes.
Yeah.
So yeah, no, that's a great thing to point out. So this graph was actually generated in Excel, and I don't show how to do it in Design Expert, but what you can do, I think someone maybe mentioned it yesterday. What you can do is copy and paste the formulas from Design Expert into Excel. And what you can do is you can play around with the different inputs and what the output predictions will be. And the reason why I did this graph is I kind of already knew what this graph was saying based on what Design Expert was telling me from optimization. But why I generated this graph is a graph in Excel is kind of the usual way of communicating within my building. And so I knew that, especially within my team, if they saw this, they would kind of immediately know what I was talking about. Because this is kind of a dosage curve in Excel is kind of the usual means of communicating. As much as the wow factor was there for taking a look at my 3D plots and all that in Design Expert, this was just a little bit of an easier way to communicate what the dosage curve comparison is between the optimized Debonder and some of the incumbents.
Great. And then Richard Williams has an additional comment on the too few runs to be trusted comment. He reminds us that proper use of the fraction of design space and standard error plots can also help alleviate some concerns about, you know, coverage and those
Yeah.
types of things.
Yeah, absolutely. And I think I pointed it out earlier, but yeah, definitely always evaluate the power of your design before you run it, and that's something I do every single design that I put together in the mixture process design space. Always look at power evaluation and that fraction design space tool for sure.
Mhm. Well, it looks like that covers the comments and questions. So I definitely want to thank you for your time today. It was an awesome presentation.